Have you ever looked at a chart, seen a sudden spike or dip, and wondered, is that real or is it just random noise? Well, in business or manufacturing, knowing the answer to that is absolutely critical. Today, we're going to dive into the hidden logic that lets us know for sure when a process has truly changed, all by using a simple tool called a control chart. Okay, so to spot these real changes, engineers use a set of rules that, let's be honest, can seem a little weird at first. For instance, one rule says you've got a signal if 2 out of 3 points in a row are more than 2 standard deviations, what we call 2 sigma, away from the average. And then there's this one. You've got a signal if 4 out of 5 points are beyond just 1 sigma from the average. Again, just look at those numbers, 4 out of 5. Feels like they were just picked out of a hat, right? And for our last example, check this out, a rule that sounds completely different. A signal gets flagged if you have 9 points, all in a row on the exact same side of the average line. It doesn't even matter how far they are from the line, just that they're all hanging out on the same side. And that, right there, is the big puzzle. Why 2 of 3, 4 of 5? Why specifically 9? You'd be totally forgiven for thinking these are just random numbers somebody made up. But here's the cool part. They're not. And figuring out why is like a fantastic piece of statistical detective work. So to crack this code, we're just going to focus on one of these rules. Let's solve the 9-point mystery. Because trust me, once you understand the logic behind this one, you'll unlock the secret to all of them. First things first, we need to understand what we're looking for a signal in. You see, any stable process, doesn't matter if it's a factory or just visitors to a website, it has a natural, random, up and down vibe. We call this common cause variation. The easiest way to think about it is just as the normal, predictable background noise of the system. And the principle behind all this randomness is actually super simple. Any single data point has a 50-50 shot of being above the average or below it. That's it. It's literally a coin flip. Heads or tails, above or below. So if every single data point is basically a coin flip, what are the odds of getting, say, 9 heads in a row? Or 9 tails? Let's actually do the math and figure out how unlikely that really is. And don't worry, the math is pretty straightforward. The chance of 1 point falling below the average is, 0.5. For 2 points in a row to do that, you just multiply the probabilities. For 3, you do it again. By the time we get all the way up to 9 points in a row, all below the mean, the probability is 0.5 to the power of 9, which gives us this teensy tiny number, 0.00195. But hang on a second. Remember the full rule. The signal isn't just 9 points below the mean. It could also be 9 points above the mean. Either one of those counts as a signal. So because the signal can happen in 2 different ways, we have to account for both of them. In probability, when something can happen one way or another, you just add their chances together. So we add the chance of 9 points below to the chance of 9 points above, and we get a grand total probability of 0.0039. Okay, now that number, 0.0039, I want you to hold on to it. It might just look like some small decimal, but I promise you, it is the key that unlocks this whole system. So what does this number really mean? It's the probability that pure random noise, that normal background static, could accidentally arrange itself into that specific 9-point pattern. In other words, this is the chance of a false alarm. So does that number seem familiar at all? If you've ever done any work in quality control, it really should, because it's incredibly close to the false alarm rate of the most famous rule in all of statistical process control. And that, of course, is the classic 3 sigma rule, the big one. The idea that if a single data point falls way, way out there, beyond 3 standard deviations from the average, that's it. That's a definitive signal that something special, something not random, is going on. And here it is, the big reveal. The probability of a false alarm from our 9-point rule is about 0.0039. Meanwhile, the chance of a false alarm for the 3 sigma rule is about 0.003. For all intents and purposes, they're identical. Now, this is not a coincidence. This is the whole elegant design philosophy that's been hiding under all those strange-looking rules. They aren't random in the slightest. They are meticulously calibrated. So, here's the big takeaway. All those rules, the 2 of 3 points, the 4 of 5, the 9 in a row, they were all mathematically designed to have the same very low chance of happening randomly as a single point falling outside those 3 sigma limits.
They're like a team of specialized detectors, all looking for different kinds of changes, but all calibrated to the exact same level of sensitivity. And this is what makes it so powerful. It means when you see any of those signals on a control chart, you can act. You can be confident that what you're seeing isn't a fluke, because the odds of it being one are incredibly low. We're talking just 3 or 4 times in 1,000. You know something real, something special has happened to your process.
Of course, this really just pushes the mystery back one more step, doesn't it? We know all the rules are based on the 3 sigma idea. But why 3 sigma? Why that specific probability? Why did the guy who invented all this, Walter Shewhart, choose 3 sigma in the first place? Well, that is a fantastic question and a story for another time.